this is the Boolean question, question number 3 from the weekly worksheet. This question is pretty challenging in my opinion, and yeah, this clip is going to show you how it could be done. So we're going to approach this problem using dynamic programming. Yeah, let's read the problem first. So we're given a list of balloons, and we have to pop them one by one until all of them are gone. And for each balloon that we pop, we get its value times the value after and times the value beforehand. And the beginning and the end would treat it as a 1 printed at the -1 or n+1 position. So what we can do is that to compensate for the beginning and the end case is for nums, we can set it to 1 plus num plus 1. And that has the beginning and the end. And we notice that if we think about the forward logic in 3158, if we take out, for instance, if we take out 5 at first, then the DP would guide us to find the answer for 3, 1, and 8. But that's an issue because after removing 5, 3, 1, and 8 will be connected together, and we wouldn't have the information for that. And if we actually have the information for all of the subsequences, that would solve the problem. But there will be 2 to the n of those, and that will be very slow. And in this problem, we're aiming for O of n cubed solution. So what we can do is just think about the other way. At any position in DP, instead of thinking that we're going to remove this one first, what if we remove all the other ones before we remove this one? Let's say we want to remove 5 last. Then in that case, we wouldn't have to worry about 3, 1, and we wouldn't have to worry about 8. And it would simply be the case of 1, 5, 1, where there are paddings of 1 at the beginning and 1 at the end. So that's the case where 5 is removed last. In that case, 5 would serve as a separator between 3, 1, and 8. And if we know the same idea for 3, 1, and for 8, we can just sum it up, and we know the optimal value based on building a DP. So what we want to do to store in our DP is to store the values, not so for instance, this question, if we do DP of 0, 2, we want to find the best solution in between 0 and 2, non-inclusive. And the only possibility right here is 1, the position 1, which is 5. And that's just popping 5. 1 times 5 times 1 equals 5. Yeah, so we're always looking for places not considering beginning and not considering the end. It's always exclusive. Okay, let's try to build the DP array. So first we should initialize we can set n to be the length of nums, and we can initialize a 2D array of n by n, all value to 0. That could be the first step. And then to start building the array, what do we have to consider about? In the 2D array, we want the first entry to be the starting index, and the last entry to be the ending index. And what we want is that we should include the start and the end, and we want to find the optimal value in between the range that's given. Okay. I don't have a solution next to me, but let's try to work it out together. So how do we build a DP array? Yeah, let's call this array DP. What we can do is that we can do a for loop. Let's call it K. And let's define K to be the distance between the left index and the right index. And we know that the distance has to be at least 2 away, because if they're 1 away, we're not including the starting and the end. There will be 0 element in between, and that's pretty pointless. So we want there to be at least 1 element, and that requires a distance of 2 away. So the starting range is 2, and the ending distance should be n minus 1. So it's from 2 to n. That's the possible distance between the left pointer and the right pointer. Yeah, so n minus 1 will be the case with the left pointer being the leftmost one, and the right pointer being the rightmost one. And then we can run another for loop for I in range n. And this will try to go through every row. And for each row, there should be a corresponding value of j, which is the right index. And what does j equal? J should equal to I plus k, because we know that there are k distances away. So we should set j to be I plus k. But there's also an issue, because after adding k, j could be out of range of n. So if j is out of bound, break. So we don't want j to be out of bound. We would just move on to the next row if j is out of bound. And then we can start setting the value of dp of ij, but we have to consider every single possible split. So we from the length of I to j, for each of the possible number in between, we have to consider, what if we take out that number last? Then what would be our best number? So dp ij would equal to the max of so we define a split. Split has to iterate from I plus 1 to j minus 1. So it would be for split in I plus 1 to j in range. And for splitting range of that, we want to compute the max. And how do we compute the max? As we said, because we're removing the value as split last, we're separating it from left and right side. the left side is very simple. It's just dp of I to split. And that's the left side. And the right side would be dp of split to j. And we know that split and j are both non-inclusive. And for the middle part, so we'll be taking a split last, and it would simply be dp. Not even dp, we can just take the number because sorry, I'm running out of space. I'm gonna write it right here. So if we want to take a split last, split would just be nums split that's the value we're taking out, multiplied by the number beforehand. And we know that the number beforehand would be nums about this. If we take out the number last and we would have already taken out the left side and the right side. So number of I and number of j would actually be the number left on the left side and right side after the other part taken out. So we put this right here. So in this case, we would try out every single option that could be split it and find the maximum of them to put in the dp of ij, where I is the left pointer and j is the right pointer. And this would be done recursively until we build all the necessary ones. And because we're defining I from 0 to n and j to be the difference of I plus k, when we put in the dp, we're actually only using the upper right triangle, and we start filling in values like this until we reach the end. This is a case of dp 0 and m to n minus 1, and that is a case where we consider all of the numbers, including the padding from 1 to 1. So in the calculation, these two will be ignored, and we'll have to find the optimal value for these numbers. So because of that, we can just return dp of 0 to n minus 1. And for the time complexity, instead of the O of 2 to the n before solution we talked about earlier, this part is O of n, this part is O of n. And don't forget that because we have to try every single split option, and this could technically go up to n times, because at first there's not many split options. It would be one split option and then two split option all the way up to n, and this equals n times n plus 1 over 2. So this part is still O of n. So overall, we would have a nested loop of O of n. There are a total of 3 loops. So time complexity, it ends up to be O of n cubed. And the space complexity, we're just storing the 2D array. So space complexity would be O of n squared. And that's it. So the main part, the difficult part, would be considering the left side and the right side. That we have to do it exclusively, not storing the leftmost and the rightmost. And that's one thing. Another thing is that we cannot use the forward logic of thinking, what happens if we take this one out first instead we have to think about what happens if we take out this one last. And that's the only way to separate the left side and the right side. In that way, we can just use the value of dp from the previous iteration, which would be available because like the range of this would be shorter than the range of the whole thing, right? And as such, we would build the whole array. And the reason we're building the array diagonally is just to make sure that when we have a array of length 4, if we split right here, that's the maximum number that could be computed afterward, which is always less than the current difference of j minus I, and that's already computed because j equals I plus k, and k is always increasing. By the time we get to j equals I plus k, we have already computed I plus k minus 1. So it ensures that all of the values that we need for these computation right here is already included. And yeah, and that should be it.